So I've got a performance bug in this simple web application called the door game. Behind one of these doors is a prize, and if I select the right door, I get the prize, otherwise I lose. And I do get a second chance if I select the wrong door. The prize location will randomly be reassigned, and I can either stay with the current door or switch to a new door. In this case, I lost because I switched to door 1, and the prize was in door 2. Now, the performance issue occurs anytime I switch to or stay with door 3. Notice when I selected stay with door 3, it took about 5 seconds for the outcome of the game to be displayed. And in that scenario where I was switching to door 3, there was also about a 5-second delay before the outcome of the game was displayed. This game is currently being hosted on a Kubernetes cluster on a VM. Thankfully, we've instrumented this game with the Splunk OpenTelemetry Collector, and we didn't have to manually instrument it because this is a Java application using the Spring framework, so it's supported by zero-touch instrumentation. All we had to do was install the Splunk distribution of the OpenTelemetry Collector and restart the application to send metrics, traces, and even code profiling data to Splunk Observability Cloud because we've enabled a feature called AlwaysOn Profiling. Let me show you how quickly we can identify the root cause of this performance issue by using the AlwaysOn Profiling data in Splunk APM. From the home page, I'll navigate to APM. From the APM overview page, I can see this chart called Top Business Workflows by Duration. These are custom workflows that you define, and they represent critical paths that users take through an application like a login process, adding an item to a cart, or completing a purchase. And there's one business workflow that stands out with the highest duration among all of them, and it's this outcome workflow. So let's select that outcome workflow. From here, I'm going to select the Traces tab. And in the Traces section, there is a list of long duration traces, and it looks like their duration is around 5 seconds. So I'll select the most recent one. So in the first span, we see 8 call stacks, and in the second span, we see 51 call stacks. And that indicates that most of the duration of this trace was from this span. And if I select this span, I get the span details on the right-hand side, and then I also get a tab for the profiling data, specifically the CPU stack traces. From here, I can navigate directly into the AlwaysOn Profiler by selecting span. So the trace waterfall allowed me to identify generally where the latency was located within the request. But to really understand why there is latency, I need to know the exact line of code that is the source of the latency. And that's why we need AlwaysOn Profiler, because it gives us that exact data. On the left-hand side, we get a list of stack frames, the amount of time that that function took on the CPU, and the number of times that that function was invoked. And on the right-hand side, we're getting a flame graph that is aggregating all of the data from the stack traces and giving us an average duration of each stack frame. If I filter the stack traces to only the ones that include the sleep function, which appears to be the function that consumed the most amount of CPU time, the flame graph is then filtered to just those stack traces. And we can see the thread sleep function at the bottom of the stack, and it looks like the first function that is calling that sleep function, besides this utility class that defines the sleep function, is this precheck function in doorchecker.java on line 36. So now we know exactly where to look in our code base to identify the source of this performance issue. I'm going to pull up the code base in VS Code. So what we're looking for is the doorchecker.java file, and then line 36 in the doorchecker class. On line 36, we see this sleep function called with a value of 300 plus this extra variable. What is this extra variable? Well, the extra variable is calling the power function, and the two values that are being passed in is the number 70 plus the door number that's being selected. Now these door numbers are 0 index, so the possible values here are going to be 0, 1, and 2. This precheck function is only called during the final decision of the game. So when we switch to a door or we stay with a door. If we select door number 0, then the extra value is going to be 1. If we select door number 1, then extra is going to be equal to 70. But if the door number value is 2, which in the user interface is actually door number 3, then this extra value is going to be 4,900. So 300 plus 4,900, which is about 5 seconds for the sleep function. So this is the source of our performance issue, and it is an arbitrary example because why would we need this extra variable to begin with? We can directly delete line 35 and the reference to the extra variable on line 36. Now that I've saved this code, I'm going to run a quick script to redeploy the application, and then we'll test our changes. And it looks like the game was successfully redeployed, so let's take a look at it in the browser. I'll select door 3, and then I'll stay with door 3. And you can see that even though we stuck with door 3, the outcome of the game was returned immediately. And this time I'll switch to door 3. And again, when we switch to door 3, the outcome of the game was returned immediately. And we didn't have that unnecessary latency when switching or staying with door 3. And thanks to AlwaysOn Profiling, we were able to quickly identify and fix the root cause of the performance issue. With Splunk AlwaysOn Profiling, you no longer have to guess what's causing performance bottlenecks in your production environments. I hope you enjoyed this video, and if you did, we'd love to hear your feedback. And if you're interested in trying Splunk Observability Cloud yourself, you can navigate to this link to claim your free 14-day trial. Thanks for watching.